Hello everyone, my name's Aiden. I'm joined here today with Aaron, Matthew, and Wenyu. Today we'll be presenting our product, the Aim4Pass. Aim4Pass, A4P for short, was created to solve a problem with hockey training. Currently there is a large gap in the available training products for hockey. There are no dynamic tools for arguably one of the most important skills, passing. The A4P plans to change that with a dynamic passing robot that will keep the player moving, their head up, and make them read the situation around them and react to the changing targets. The AFLB drills will mimic real game scenarios where the player needs to react fast to volume plays or recover from mistakes/poor passes. In a typical drill, the AFLB will set up and targets will be randomly spaced in the target zone. The player will then skate around while the A4P tracks the player. When the player receives the puck from the A4P, a random target will light up. The target will then have visual cues to tell the player roughly how much time is left to score, and it will also display if the target's missed. All of the information is relayed back to the A4P to track the player's progress. There are several design requirements for the A4P. These requirements were obtained through a thorough stakeholder consultation. Most of these requirements have been met by the current prototype, however testing on the reliability remains incomplete. The first requirement is capacity, as we don't want to be constantly refilling the A4P. Next, the targets need to be able to communicate over the entire training area. The device also needs to be reliable and impact resistant, while accurately and quickly passing the puck. Finally, the device needs to be easy to take to and from the training area. Now we're going to talk about design. Our device is broken down into three main features: the robot design, the net design, and the software design. The first component is the dispenser. There are several proposed solutions for puck storage. However, we decided to choose the 4-silo method because of its small form factor and reduction of mechanical components. Each silo can hold up to 6 pucks, which fall into the orange rotating disc powered by a gear and stepper motor. The disc rotates and drops the puck launcher. Here is a short video of the dispensing system dropping the puck. This video is from testing the step size, and therefore it pauses approximately every quarter turn. To determine the power requirements of the motor, we took a free body diagram of each silo. The net force required was 42.5 newtons. However, due to the geometry of the rotating disc, we achieved a gear ratio of 5.5, which gave us a torque of just over 10 Newton meters, which doubled the required torque.
After the puck is dispensed into the robot, it enters the launcher, which is responsible for accelerating the puck to pass it to the user. It consists of the wheel, motor, motor mount, shaft assembly, and slope. We sized the motor from calculations that estimated the torque and speed requirements to achieve a maximum speed of 70 km per hour. The motor is coupled to the shaft using a flexible motor coupling, which allows for slightly offset installation. Pillow block bearings are used as they allow for simple assembly onto the aluminum extrusion. The reason for designing the launcher in this way was that it provides the largest energy transfer to the puck, while relatively having less components and being easy to assemble in comparison to other potential designs. Throughout the design process, there have been many design improvements. One of these is the use of aluminum extrusions and a motor mount for the shaft assembly, which was a lot easier to assemble than the previously designed C-channels, as they are attached in the same way as the rest of the frame. Also, a pneumatic wheel was used instead of the rubber wheel, as it is able to compress and create a larger contact surface area to transfer energy to the puck. This video shows the last test run we conducted on the launcher. As shown, we were able to easily reach a speed of approximately 15 km per hour, even with the motors being run at approximately 1/6 of the max speed. The last mechanical component is the chassis, which is built to house and act as structural support for the other components. The chassis is fully built from aluminum extrusions, which have a high stiffness and strength. We calculated the deflection that could occur on an extrusion under a full load of the robot, and it was less than 1/100th of a millimeter. Using this material allowed for simple assembly and deconstruction, which is very useful while adjusting the alignment of components. Attached to the bottom of the chassis is the rotation assembly, which consists of a lazy Susan bearing attached to a gear that acts as the base of the entire device. A motor coupled to the pinion gear moves and rotates the robot. The rotation assembly was changed from wheels to the lazy Susan, as eliminating many components and cut down the cost significantly. Additionally, there is less alignment requirements and less points of failure. Here's a video of the robot during one of our tests. There was some misalignment due to the pinion being 3D printed using resin and manual alignment, which means that the pitch circles were not exactly tangential.
Now that we can shoot the puck and aim the device, we need to track the player. Tracking the player consists of three parts: calibration, filtering, and calculations. Calibration begins with setting up the stereoscopic cameras at a fixed distance apart. An object with a fixed pattern is used to feed the algorithms congruent images from different perspectives. In this case, a chessboard with known dimensions is used. Stereo photos are taken from every angle and location within the field of view. These image sets, along with the focal distance of the cameras, are fed into an algorithm which determines the radical and tangential distortion resulting from the intrinsic properties of the stereo camera and creates matrix filters to account for the distortion. These matrices are used during the disparity calculations. Once the calibration is complete, the stereo cameras are ready for player tracking. The left and right images are fed into a color filter, which filters for a specific jersey color, in this case, red. Then, the center of the jersey is determined. The calibration matrix filters are then used to project the image taken onto a common plane, also known as image rectification. Then a three-way semi-global block matching algorithm, also known as SGBM, uses the rectified images to predict the distance of the objects in the field of view. This is done by comparing each pixel in the left image to the estimated location of the pixels on the right image and the approximate pixel shift. This video shows the point cloud projection of the resulting disparity filter. Notice how the jersey is on a separate plane from the room and the door. The depth and angle of the player relative to the camera is then used in the next stage, calculations. The distance and the angle are fed into a Kalman filter, which has been calibrated with a simulated acceleration model of a skater on ice. Using the model and calibration data, the filter estimates the joint probability distribution of the angle and the distance. The algorithm predicts the next location of the skater, and once the new readings from the disparity filter are calculated, they are compared with the predicted values. The algorithm recursively corrects for the inaccuracies. This reduces the sensor noise and variations in the disparity calculations. The resulting calculations are used to predict the skater's trajectory, velocity, and acceleration. This data is used to center the Aim4Pass and to determine the pass speed and offset angle required for tape-to-tape passing.
Here we have the SmartNet. The SmartNets are controlled by a Node MCU, which sits just above the connection bar, and uses Wi-Fi to communicate with the A4P's Raspberry Pi. The SmartNets use a line laser and receivers to detect a puck crossing into the net. The net includes RGB lights to visually show which net is the active target. A blue light is shown once the net is active, and turns light blue when half the time limit is gone. A green light denotes a goal, and a red light denotes a miss. In this video, we demonstrate missing the net. So, the drill is started when the blue light turns on. Halfway through the drill, the light blue light turns on, and then after, the red light will denote that the player has missed the net. In this demo, we are testing the reliability of the net, as well as the light sequence and scoreboard mechanics when a goal is scored.
I'm going to go over our user interface. Instead of using a touchscreen, we've decided to set up a web server on the Raspberry Pi and allow the user to interact with the robot with their phones. There are a few advantages this design provides. First, the user can control the robot remotely. So if you want to stop the robot during a training session, you don't have to risk your life dodging from a robot trying to shoot pucks at you, and try to stop it from a screen at the back of the robot. And even though it sounds like a lot of fun, we've decided not to include this feature in our product. Second, a website is cross-platform, so you'll be able to access it from any browser in any device as long as you're connected to the same network as the robot. So here's our GUI. As you can see on the left, that's our homepage. You can start our training session, go into manual mode, or configure some of the parameters of the robot. When a session starts, you'll see the middle page. Basically, you'll be able to stop a session halfway through. If you manage to finish the session, a scoreboard will pop up and show your performance data, including how many shots were fired, your accuracy, and the average response time. On the left is our manual control mode. This allows another person to control the robot through the website. You can launch pucks and change where the robot is aiming at. So you can basically interact with another player. In the configuration page, you have access to some training parameters as well as being able to test the motors on the robot individually, and that's mostly for calibration and testing purposes. So in the training configuration, you can choose how many pucks you want in the session. You can also change the difficulty of the session. The more difficult a session is, the shorter the duration the net will light up, which means you have less time to pass the puck into the net. You also have access to different motors on the robot, and they're mostly for testing purposes. So here's a quick demo. We're using our GUI to speed up the launcher motor. So basically, the training session is basically the only part we didn't get to implement. As of now, the GUI is able to control all the motors and works pretty well.
The cost of materials to produce the Aim4Pass is $1,410. The most expensive items were the electronics required for stereoscopic tracking, the aluminum extrusions, motors, and motor drivers. However, the material costs only account for about 1% of the estimated total production cost of the device. We estimated that the project required about 800 engineering hours, and at a rate of $100 per hour, this would have been the largest expense, totaling $80,000.
The project schedule for Term 1 is shown. Subtasks in blue represent engineering tasks, orange for administrative tasks, and green for manufacturing tasks. The project began in September with 3 weeks of problem definition and stakeholder analysis. Then began 5 weeks of solution generation, prototyping, and solution evaluation. The end of October consisted of 2 weeks of procurement researching and ordering of long lead items. In November, the team split up into 2 groups. The software team worked on player tracking, communication, net control, and user interfaces. Meanwhile, the mechanical and electrical design teams worked on the CAD design and ordering all remaining materials. Term 2 saw the machining and assembly portion begin with the mechanical and electrical team finishing up the CAD drawings. In February, calibration and testing began with the integration of the assembled device and software components. However, due to the UBC shutdown in March, this was only partially completed. The original plan was to complete final assembly tasks, implement aesthetic and safety improvements, and prepare calibration and demonstration for Design and Innovation Day during the remainder of the term. The additional work we anticipated to complete includes implementation of current sensors to prevent motor stalling, testing the reliability of tracking, integrated testing of all robot and net components, and ICE testing. Further down the line, future improvements would include gaining user feedback, upgrading the launcher motor, adding additional preset training drills, upgrading the shell of the robot to a less brittle material, and upgrading the gears to improve wear resistance.
In conclusion, the A4P solves the problem with current training devices, while creating endless possibilities of new ways to train. I'd like to thank all of our stakeholders, and thank you for taking the time to watch this presentation. Have a great day.